Hello everyone. So this is a video lecture going to be on principal component analysis. We all know by listening this, many of us Pythonistas mostly, they start from scalar, decomposition, import PCA and all the stuff. But I would like to go through the math that is behind this principal component analysis. Hope you would all like this. Let us start. First of all, let us focus on some prerequisites. First of all, two things: L square norm and the Frobenius norm. I mean, L square for the vector and Frobenius norm for the matrix is required. First of all, some elementary knowledge of matrices is required, which I'm not going to cover as such. I'm assuming that you know those stuff like eigenvectors, matrix transposes, trace, and all those stuff. Next is derivative of a scalar with respect to vector. This is going to be covered. Next is eigendecomposition of a real symmetric matrix and its use, which would be extremely essential towards the last part of the proof. And one tip, have a pen and a paper beside you and enjoy. Let us begin. First of all, let's cover the L square norm and the Frobenius norm. So the heading is Frobenius norm, but L square norm is defined for a vector as root over of x transpose x, as you can see here. It is defined as root over of x transpose x. It is also termed as Euclidean norm. Basically, there is a definition of LP norm where it is actually summation of all the individual elements to the power p and taking its 1 by pth root. So if you want, I can write the formula. You take its power p and then sum over, like we do for squares, sum over, and then take whole 1 by pth power. And this is for all, like means we take it for all the elements. This is basically, if we take p equal to 2, that is what we get L2 norm. This is LP norm. And this is also known Euclidean norm because for coordinate geometries, as we know, the distance of a point from the origin is defined as the Euclidean distance. That is why. This is the distance of a vector from the origin, where origin dependent in the pth dimension. Fine. Next is the Frobenius norm of the matrix is extremely similar to the L2 norm. Fine. So that it is defined as this thing, denoted by AF written below there. That is equal to root over of summation of a square ij. This is the aijth element. Fine. And further, if you can manipulate this a little bit, you will find that if you multiply A and A transpose and take the trace of the resulting matrix AA transpose, then that is exactly equal to the Frobenius norm of the matrix A. Why is this so? Because simply you have to think a bit, pause maybe, and try to work out. Multiply A and A transpose, take a small matrix and see that after finding the trace of AA transpose, we're just basically getting the sum of the square of each elements, which is exactly equal to this thing. Means what I'm trying to say is that the sigma of A square ij is going to be exactly equal to this term, the trace of AA transpose. Just pause and try. It's not a difficult task. Fine. Next we come to derivative of a scalar with respect to vector. We all know the derivative of a function with respect to one variable. Let's say dy by dx, where y is represented as fx, or even we also know the partial differentiation. For instance, dou, what we represent, for instance, like this, not exactly d. Fine. So here this y is a function of x as well as some other variable. So that is why we represent the partial differentiation of y with respect to x, and we define it as the differentiation of y with respect to x, keeping the other variables as constant. So here similarly consider two vectors, x and a, both a p-dimensional vector, means in the Rp, means they both belong to Rp, this x and a scalar y which is defined as x transpose a. So we are getting, this is 1 cross p, p cross 1. So we are getting a 1 cross 1 matrix, and that is basically simply a scalar. That's not a matrix to say as such. Now, so if we try to expand it, let's say x is denoted by this x11 and then dot 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 xp1. We can say this as the matrix x. Okay, I don't require to write that one latter. Don't worry. Only x1 to xp works. 1 is just because the column, and next is a11 and so on till ap1. Fine. This can be printed as a, this can be printed as x. So these are two p-dimensional vectors, and after multiplying x transpose a, we are going to get this thing. Fine. x11 a11 plus till xp1 ap1. Fine. Now we would like to find the derivative of a, say, with respect to x. Fine. Then first of all, we should ensure the dimensional correctness, means whatever the resultant vector is going to be after we find the derivative of a scalar with respect to the vector, then the final dimension of the vector that we obtain is going to be the same as that of the vector with respect to which we differentiated. This means that after doing dou y by dou x, I'm saying dou because a is another vector is there. So dou y by dou x should result in a p by 1 vector, which means a p-dimensional vector. Now that is what I have written here. This means after the result should have the dimension same as that of the vector x, that is p comma 1. After differentiation with respect to x, we would obtain a, which is a p-dimensional vector. Now how we obtain this, I'm going to show that in the next slide. But remember, the result finally is going to be this vector a only. Means what I want to say is that if I find dou y by dou x, where x is the vector, y is the scalar, I'm going to get a here. Fine. So this is what the result is, little factor dou y by dou x is equal dou y by dou x11. Remember the x matrix, I mean the vector x was represented as x11 till xp1. So if we want to find the derivative of the scalar y with respect to this vector, then what we do is that dou y by dou x1 dot 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 till dou y by dou xp1, and clearly see that this is a p comma 1 vector. Fine, p-dimensional vector belongs to Rp. I'll be attaching some links to understand this in more detail. Don't worry about that. You can go through those links also in the description below. And this is exactly equal to this thing, because by definition we know that y is equal to x11, a11, and so on. So if we differentiate y with respect to x11, then what we are getting is a11. So this is what is the first thing here, a11, the first element. Yeah, and as you continue, you can try it out yourself. You are going to get a only. Okay. This is one example I have given. The theory a bit here it is given. If you want to go in more detail, I'm going to attach links in the description. Don't you worry about that. Next comes eigendecomposition, and it assumes that you know eigenvectors of matrices. So every real symmetric, the first thing is that every real symmetric matrix can be decomposed into an expression using only real valued eigenvectors and eigenvalues. For Q in this expression, this is actually the eigendecomposition of the matrix A. It is actually the actual eigendecomposition of any square matrix could be some let's say Q, some diagonal matrix, and then Q inverse. So, that handwriting is horrible, I know. So Q diagonal, some diagonal matrix Q inverse, and so this is exactly what this is the diagonal matrix here. The thing is that this Q and Q inverse is there here. Q and Q transpose is there. So Q inverse is Q transpose. Hence we are saying that Q is a orthogonal matrix, and this is for the real symmetric matrix A. Fine. Now consider the quadratic expression fx equal to x transpose ax, subject to the L2 norm of the L2 norm of x being 1. The vector x means what I am saying is that this L2 norm, it is represented by double mod and then 2 below. 2 means L2 norm. This is equal to 1. This is the constant, and the quadratic expression given is fx equal to x transpose into a into x. Now mark that whenever x is an eigenvector of A, then the functional value is the corresponding eigenvalue. Why? Because this ax is going to be, let's say the corresponding eigenvalue is lambda. So this is going to be lambda x. Lambda being a scalar can come out. So lambda x transpose x, and x transpose x is the definition of the squared L2 norm, means the square of the L2 norm, that is 1. So this value is going to be lambda. So under constraints, the maximum value within the constant region is the maximum eigenvalue, and the minimum value is the minimum eigenvalue. Remember this point. This is going to be extremely useful during the proof ahead. Now, so I guess we have covered all the required prerequisites. It may be fast, but let's move to the fun part. So now let us move to the PCA. Yay! So what do we know PCA? PCA, just let me remove this a bit. So PCA is exactly, it is used to compress the input data in machine learning. For instance, I'm giving one example in machine learning. There is a set of data, let's say x, represented as x, not a vector, but a matrix. So what we get is that we want to compress the data without losing much of the variance that is already present in the x. So we try to reduce it. So we try to project the data into a smaller dimension. For instance, let's say x be a n dimension. I'm taking one data. Clear? I'm taking one data. Let me write it a bit. I'm taking one data. Let me term that x1, and this is belonging to Rn. Let's say, and this is an n dimensional vector, means n features, if you may say, n features. And we want to compress this, or we want to find its encoding in a lower dimensional space. For instance, I'm going to find its encoding as fx equal to c, let's say, in L dimension, where L is less than n, so that I can obtain the data in a less memory space and also avoid losing much of the variance. So this is important. We don't want to lose much of the variance that is present in the x, and also we want to store it in less occupying memory. Fine. So what we want to find an encoding of vector x as fx equal to c, and a decoding function g that provides x nearly equal to g of fx. This fx is in the L dimension, and after taking the decoding function g of that L dimensional vector, we are going to get back as much close as to x. The encoding and decoding might give rise to certain loss. Thus, we want that loss to be as less as possible. So this is our main objective, overall objective. Means after decoding, we should get as much close to x, which means that we are not losing much of the variance obtained in the present in the x. Now, let x be n dimensional as I have stated, and c be L dimensional. To make the decoder simple, means decoding of the L dimensional vector, we just want to present a matrix multiplication here, g of c equal to d into c, where d is obvious. This is L cross 1. Let's say this is a vector, and this should be n cross L to obtain finally n cross 1 vector. Means g of c is giving back me the nth dimensional vector. Now, to make the decoder simple, we are considering this as a matrix multiplication. And further, to keep the encoding problem easy, we consider the matrix D to have each column orthogonal to every other column of D. Though the matrix may not be square and hence not orthogonal as such, because for orthogonal matrix, the definition is D transpose D equal to, let's say, I of that dimension, whatever. But here D is going to be square matrix to be orthogonal. But here the D may not be square matrix because N and L are different mostly. So we just say that we consider the matrix D to have each column orthogonal to any other column of D only. And for uniqueness, we consider that each column of D has got unit L2 norm. Now, why unit L2 norm? For instance, it can have any norm. Let's say a vector has norm D. Then we can find another encoding by just dividing it some factor and multiplying the vector C by another factor. For instance, I can find if it is, let's say there is no constant of unit norm. So I am taking each vector as of norm, let's say D. So this can be D by D into D into C. So I have found another encoding for this x dimensional vector, n dimensional vector. So for x, I have found another decoding, this D into C, encoding D into C. And so this can vary, like I can change D to another thing, and then this D would change, because I'm just multiplying, that scalar would cancel out and it would finally give me G of C equal to D into C. So therefore, to keep this, keep a uniqueness to the matrix D, what we want is that each column of D has got unit L2 norm. Fine. Now, here comes the first task. Keep your pen and paper ready. So how to get the best C? Okay, how to get the best C? Yeah, C star, let's say that be the best C. Fine, it is in the L dimension. Now, how can you obtain C star? C star equal to argmin, means minimum of all the C present in the L dimension. And what we want to minimize? The x minus gc norm, L2 norm, because x minus gc is a n dimensional vector. So what we are trying to say is that I want to minimize the squared L2 norm of this vector, this x minus gc, because gc is what we obtain after decoding, means after multiplying the matrix D into C and obtaining in back the n dimensional vector. C, remember, is a L dimensional vector. G of C is a n dimensional vector, which is almost as close as to x, so that PCA works. because we don't want to lose much of the information. Clear? So that is why it is. So what our aim is to minimize the squared L2 norm of the vector x minus gc. Only L2 norm works, but squared L2 norm, because that would make things simpler later. There is no root over stuff. So x minus gc, it can be represented as this thing, because I have defined earlier L2 norm of a vector x is x transpose x root over. So squared L2 norm is going to be x transpose x. Now this is what we get, x minus gc whole transpose into x minus gc. Now here to here is a large jump, it requires a lot of calculation. So bear with me a bit. So just try to simplify this. There is nothing much of any rocket science stuff. So this is going to x transpose gc transpose, just transpose rule, a plus b whole transpose is a transpose plus b transpose, and x transpose x, what we are getting is x transpose x first of all, then x transpose g of c, next is minus g of c transpose x, and then plus g of c transpose g of c. Fine. Now first of all, notice that we are minimizing over c. This stuff is of no help. Now what remains is x transpose gc and gc transpose x. Mark one thing, that x is n cross 1 and gc is also n cross 1. So this stuff is finally going to give me a scalar thing, this stuff, and this stuff is also going to give me a scalar thing. A scalar and its own transpose is going to be equal. So what we get is minus twice, let's say, x transpose gc plus this thing. Fine. So this is what we obtain. Now let us try to use the fact that gc we have decoding as d into c, a vector into c. So this is x transpose dc, and that is what we obtain here. Fine. And this is dc whole transpose dc. So this is c transpose d transpose dc. Now this d transpose d is going to be a I or means identity matrix. So this is c transpose c finally we obtain, because every row, every column of d is having unit norm and is orthogonal to every other column. So d transpose d is going to be a identity matrix. So this is going to be c transpose c. Clear? So that is what we obtain here. We have to minimize over c minus 2 x transpose dc plus c transpose c. Now this is coming out familiar. So how to solve this thing, we know from calculus that we try to find the differentiation of this stuff with respect to c and then equate it to 0. What we obtain is the final answer. Fine. So how to obtain the differentiation of this entire stuff? First of all, let me erase this thing. You can skip some time ahead because erasing might take some amount of useful time. Okay, fine. Done. Yeah. So first of all, let us consider this c transpose c. What we are going to obtain is c11 square plus c21 square plus till cl1 square. Clear? Now what we have to do, we have to find the derivative of this scalar with respect to the vector c. So what we should obtain finally is a L dimensional vector. So what it will be? So first element would be 2c11, second would be 2c21, third would be 2c31, and then so on till 2cl1. So taking common 2, we are going to get twice of c. So this is going to give me, after differentiation with respect to c, twice c. And clearly, if you try to work it a bit, consider x as a n dimensional. So this is going to be 1 comma n dimension, and d is a n cross l dimension, and then finally c is going to be l cross 1 dimension. So finally this x transpose dc is giving me scalar again, and I have to find the derivative of the scalar with respect to vector l dimensional vector c. So what I am going to obtain finally is also l dimensional vector, and this minus 2 is going to stay as minus 2. So minus 2, and if you differentiate this, what would be the first element? The first element of the resulting vector would be obtained by differentiating the scalar with respect to C11, keeping all other constant. So what is the what is the coefficient of C11 in this product? It is going to be D transpose X. Why D transpose X? This is just because we have to find this L cross one dimensional vector. You might find this is X transpose D, but X transpose D, but what we want is a L dimensional vector, so it would be D transpose X. So that we obtain finally, and so final thing is twice of D transpose X plus twice of C is equal to 0. So what we obtain finally is C equal to D transpose X. So the PCA reconstruction operation could be represented as R of X, that is equal to G of Fx, and Fx is simply C. So G of C, so D into C, and C we obtain as D transpose X. So the final thing is D into C, D into D transpose X. Let me clear this space and move on to the next one. And the next one is we have to obtain the matrix D. Now we have obtained C. Let us move ahead to find the matrix D. Now first of all, we have to choose the matrix D by solving the following stuff. Remember one thing, that the matrix D, each column cannot be considered at a single time. Means I cannot consider D first column in isolation from D second column, because I'm using all the L dimensional vectors, means all the set of C that have been obtained after encoding the original n dimensional X vectors. I am multiplying all those L dimensional vectors with respect to D only. So I cannot consider each column of D in isolation. I have to consider the entire matrix in one go. So what I have to do is let D be that matrix which I require. D star equal to R minimum of D, and this stuff we have to. And how I obtain this stuff? This is obtained due to the fact that we have to minimize the Frobenius Norm of the matrix of errors. Now let us consider matrix of errors. What are the errors? After reconstruction, what we get? And this is before, this is after PCA reconstruction, and this is the original data that we have been given. So this we have, so the error is going to be this thing. I guess I have missed this square here. You can take square or not, that doesn't matter. We have to finally take the mod of it. Let's take the square, that is of no issue. So this is if you don't take the square, that is also of no matter, but square is for best. Fine. Subject to D transpose D equal to IL, because D we have considered as an orthogonal matrix while encoding. So let me pause a bit here and let the floor open. I would give a part 2 for this PCA stuff, the proof that what we are going to obtain D. So that is there for you in the next part. So stay tuned and enjoy that. Let's meet soon.